Hey, good morning, Rala. Morning, everyone. How are you guys doing? Doing great, I guess. Okay, so let's get started. It's snowing outside, so glad to have you guys join me online. We will continue our lectures on the reinforced concrete design flexure component of it, and we'll go through how do we do the analysis of a singular reinforced section and going through the second phase, which is the multiple layer reinforcement as well. Okay, before I get started, a few things. We will have an additional time for office hour right after lecture. So if you have any questions, you have free time, please stay behind. And this office hour will be recorded, so you'll be able to see them. If you're still wondering where are the old recordings, I am uploading them. I guarantee you they will be up there in the morning. And I just need to clean up a few things in the recording, and they will be uploaded to the YouTube channel. And for the YouTube channel, I will save the YouTube link and upload it to the Canvas, so you should be able to have it as well. Okay. All right. So about homework is due Thursday, which is tomorrow. So I hope you guys are ready. And its deadline is midnight. So if you have any urgent questions, burning issues, email me today. Okay, let's get it addressed. All right. Okay. Any questions about the homework so far? Anything about the homework? Anything? All right. Well, I'll assume you guys are fine. Like I said, if you still have questions, let's reach out to me and we can set up a one-on-one and hopefully can clarify your confusions or questions. Okay. All right. Well, let's continue, shall we? So we have talked about the singular reinforced section analysis. Okay. I want you to know this is so-called analysis. Now, what is the main feature of analysis? Analysis means that if the section is given like so, okay, section is given like so, which is the blue section right here. When I say section is given, two things: the geometry of the section, which means the width of it, the height of it, okay, and then the concrete cover of it, and then the rebars, size and distribution of them, everything are known. So this is called analysis problem. So in this scenario, we're only responsible to find out the flexure strength Mn here, okay? So this is so-called analysis. So what do we do first to get analysis? We want to find out the depth of the section using the height minus the concrete cover, which is 2.5 inch, to get the depth of the beam, right? And after I find the depth of the beam, and I would now trying to find the area of the reinforcement for number 8 bars, 316 inches squared, and then total tension force is 190 kips. Okay, and then at this point, I kind of made assumption here. If you're still wondering, that is, I assume steel yielded here. I assume steel yields. All right, so that's where I made assumption already. And then tension is equal to ASFY, and that is the total tension force I have. Okay, all right, now knowing the tension, using tension equal to compression, this is from the equilibrium. This is from the equilibrium, right? I can calculate my effective compressive zone A. And again, this is so-called effective compressive zone A, effective compressive zone A, okay? And then that is the effective compressive zone A, 4.66 inch. All right, so at this point, you say, Bob, I don't know what to do. I want to get 3 points, right? I want to get a partial credit so I can pass the exam. So you will need to draw me the section diagram, which means the location of the bars, okay? Name it out, label it out clearly for number 8, and then depth of it, and draw the strain diagram, strain distribution diagram. Remember we said plane section remains plane, okay? That means you have a linear distribution of a strain and you have a actual compressive zone C. This is called an actual compressive zone C, okay? And then you have a stress diagram. When you draw a stress diagram, first thing first, this is the Whitney stress block. All right, the top rectangular is the Whitney stress block. Okay, so it has a width of 0.85 f prime c and the length of a, And be careful, this a in terms of relationship with c is that a equal to beta 1 c, beta 1 c. Okay, and then we're trying to find the tension force. And in terms of stress, this is ASFY, that is total tension force. But you can remove that, just show that stress for the steel is Fy here. Stress for the steel is Fy here. All right. And then the last but not least, add on the internal forces. That means I will label the total compression force from the concrete. And mind you that this is capital C, which is different from the small c, that is the actual compressive zone side. So that is actual compressive zone side. This is the total compression force. Total compression force. Let me just label here compressive force for concrete. Okay, compressive force for concrete. And one thing you want to be careful is that now, since we're using the Whitney stress block, right? Using the Whitney stress block, the benefit of using that is that the total compression force is located half a distance away from the top extreme compressive fiber of the concrete. Top extreme compressive fiber of the concrete. All right, so now knowing the total compression force, knowing the location of the total tension force, the lever arm, that is the distance between the compression tension equal to depth ds minus the half a minus the half a. All right, so that is everything you need to know to get your 20% grade for free. Okay, 20% grade for free. So you grab it, right? It's for free. Okay, now once I have the diagram, I will go ahead, check my strain in the steel. Okay, strain in the steel, strain in the steel. You may ask me, Bob, why do I need to check in the strain steel? I thought I have a done deal here. Well, don't forget at the beginning of the problem, we made assumption that is assume the steel yields. So you have to go back and confirm that assumption. Confirm that assumption. So where do we start? We start from the strain diagram. We start from the strain diagram, which is this fellow right here, okay? So first we find the actual compressive zone C using A divided by beta 1. And knowing that it's 4 KSI concrete, so beta 1 is 0.85, okay? And then you have A, which is 4.66 inch, and then you convert that to find your actual compressive zone C, 5.48 inch. With that, I can use a similar triangle. You say, Bob, where are those similar triangles? Well, they're here. Look, I have an angle here, and this is so-called a curvature, kappa, and I have an angle here, the same thing, right, kappa. So the tangent kappa equal to this side divided by that side, right? So I'm using that, and that is my trigonometry. Gives me this equation, and I can calculate in this equation here, epsilon cu, that is the ultimate, let me repeat, ultimate failure strain for the concrete. And you know that value, right? If you haven't remembered it, you should now. This is 0.003, okay? Remember it. I am not going to supply that in the exam, okay? And then depth 17.5, C, you got it, 5.48, and C 5.48, I calculate, and you got to strain the steel of the epsilon S, okay? This is epsilon S, I'm gonna tell you the difference later, is 0.0066, which is greater than the 0.005, and I call it tension control limit. Okay, I call it tension control limit. So to give you the full picture, where we stopped there yesterday, well actually on Monday, is that if I draw the phi diagram, the vertical axis being the phi, horizontal axis being the strain in the steel, and although right now it is epsilon S, and I just want to leave a footnote here, typically it should be epsilon T, okay? And I explain to that in the next example, but this is the epsilon strain in the steel, okay? Strain in the steel. And then I have this phi fellow here. If the strain in the steel is lower than 0.002, your phi equal to 0.65. If your strain in the steel is bigger than or equal to, let me clean this up, it's horrible writing, and then that is 0.005, right? And then you have a phi of 0.9. In between, you do linear interpolation. In between, you do linear interpolation. Okay, all right, so quick notes here. For this, right, we call this, let me use a red here, we call this boxed up, this is so-called the tension controlled limit. Tension controlled, tension controlled. The word tension controlled, meaning that the tension in the reinforcement determines the failure of the section. Okay, so only if when your strain in the steel is greater than or equal 0.005, you have a tension control limit, and that's our favorite. That is the preferred case. That is the preferred case. Okay, so if you want to take a look at this, I can start dividing this into separate cases. Okay, so if this is tension controlled If this is tension controlled, and actually this 0.002 here is also called the balanced point. Okay, balanced point. All right. So this is when epsilon t or s, in this case s and t is the same. T and s that is smaller or equal 0.002. Okay, 0.02. Okay, so now you start to wonder, okay, what had this anything to do with my section strength? Well, here's a diagram, remember? Now you look at the diagram we set here, you have this fellow here, okay? This fellow here. And I have rows, bars, 4, number 8. I have 4, number 8 bars here. And I have width of 12-inch, height of 20-inch. Remember, that is our section, right? And the strain diagram, remember, looks like this. At the top here, I have epsilon CU. And this, my friend, has been fixed, 0.003. Now, I want us to play a game. Right? Remember the plane section remain plane story. So when you bend the beam, the section rotates. All right. So if I assume it rotates to this level right here, okay, I assume it rotates this level right here, and then I say at this point, this is where the strain of steel is at, epsilon s here, equal to a 0.002. And let's approximate that equal to the yield strain of rebar for grade 60. And here I'm going to run a quiz, and quickly I'm calling somebody in the lecture to help me out here. I'm just gonna go by alphabetic sequence, okay? So let's see who's on my victim list now here. Blah, 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 blah. Andrew, Mr. Condon, are you there?
Yes.
How are you doing, man? Doing okay?
Good. How are you?
Good. You're on campus driving here in the morning?
No.
That's smart. Like that. Okay. So quick question for you, sir. You might have to help me out. So the yield strain for a grade 60, what is our value here?
1 second.
No worries. Go back, flip your notes. I understand. 0.00.
It's 60 KSI.
Say it again.
60 KSI.
60, that's the yield strength. Great. So that is Fy, right? But what I'm asking is the strain, yield strain, right? Have to divide by ES, which is, what is ES? 29?
1 second. 0.85.
No. So for ES is 29,000 KSI.
Okay.
Okay, gotta remember that, right? So now the yield strength is 60 KSI. So you do the math here, you should approximately equal to a, let me just take this out, and that is 0.00207. Here you go. Okay, remember these, okay? All right, well, thank you so much, Andrew. I think you will remember this for now, right? Especially for the first exam, okay? All right, thank you so much. All right, so we have this yield strain figured out for grade 60 thanks to Andrew, and 0.0207 is the value. So we have a situation. What is a situation? You think of it, what the strain diagram says. The strain diagram basically says that when my concrete crushes at 0.003, and give you a mind picture, right? So if this is stress in the concrete, and let me just use FC to differentiate, and this is a strain in the concrete, and I'm at actually this point here, 0.003, meaning my concrete is about to go kapoof, crushing, right? My strain in the steel just reached the yielding limit. Again, little mind picture here, you see that this is stress in the steel and strain in the steel, so it's just entering the turning point, right? So we call this situation a balanced situation. Okay, we call this a balanced condition. All right, so let me make a table here, right? So we call this the balanced condition. Okay, so how balanced? That is when epsilon s equal to epsilon y, all right? And you do this strain diagram, right? So you find out that the balance condition, actual compressive zone C divided by the epsilon Cu should equal to D as depth of the section divided by epsilon Cu plus epsilon Y. And then you do a calculation. You assume epsilon Y equal to 0.00207. Then you are C balanced condition divided by D that equal to 0.6. Means 60% of your section is in compression almost, okay? 60% of your section is in compression when you reach the balance state. That is, when the concrete crushes, you're still about to yield, just about to yield, okay? So this is the balance condition. And you should know that, right? This is in terms of phi, and let me do another drawing here, just a differential in terms of phi, okay? In terms of phi, this is epsilon S, and actually, again, let me just say T, okay? And I'm gonna leave a little mystery here, explain that later, but that is epsilon strain in the steel, okay? So here is my 0.002, here is 0.005, so here is my 0.65, here is my 0. Let me just do the dash line here, 9, okay? And now in between, you do linear interpolation, right? Linear interpolation. So this balanced point is right here. Okay. Okay, I'm just going to use a red star to represent this balance point. Okay, so that is my balanced point. Okay, balanced point. All right, now coming back to the strain diagram, right? So I say, look, what if I use a different color? See which color is good. Maybe let's use black. So what if I rotated more? What if I rotated more? I rotate how much? Say I rotate a little more, even more, so much that my strain shifted from the yield strain to a new level that is 0.005. Okay, 0.005. Okay, so when that happens, I call this under reinforced. Under reinforced. Okay, under reinforced. I'm going to use a black triangle to indicate this is under reinforced condition. That is when, okay, when epsilon S greater than epsilon Y. Okay, epsilon Y. But, okay, but when I say epsilon greater than epsilon Y, that means epsilon S is greater than 0.002, okay? But this is not correct, actually, sorry, 0.005, right? 0.05, okay? This is under reinforced 0.005, okay? 0.005. So that case, I have a C under reinforced case divided by the depth of it has to be smaller than 0.6. So when I have a much larger strain in the steel, I have a compressive zone that is much smaller. All right, so now if I can rotate this way, I surely can go the other way. So I can also rotate this way to end up a smaller strain in the steel, So for this case, I call it over reinforced. Okay, so when I have over reinforced case, my epsilon S has to be smaller than epsilon Y, that is 0.00207. Okay, so for this case, you do the calculation that my over reinforced case, the balanced actual compressive zone over depth ratio has to be greater than 0.6. So more compression. Now, if I use the square to represent the over reinforced state, right? What really happens here? So this under reinforced pretty much is going to be here, and this over reinforced case will be here. Okay, now in between, now this is the tension control limit, right? So we call this tension controlled limit. Okay, that is 0.05, right? In between, let me use a different color here to differentiate, right? Let me use orange here. In between, this is called transition. Okay, now if I do this, I can basically divide this whole thing in terms of phi into 3 zones. On the right-hand side, this is called under reinforced. Yeah, let me match the color, right? So you match the color. So this is under reinforced zone. Okay, on the left, what color I use? Purple. Okay, great. So this is over reinforced zone. In the middle is so-called transition zone. All right, so which zone are you in really just depends on the strain in the steel. Strain in the steel. Okay, now coming back to the problem. Lucky for us, we have a strain that is 0.0066 bigger than the tension control limit. Then that gives me a phi is 0.9. And this is what? Which zone are we in? Which zone are we in? Okay, I'm gonna call my next victim here. Who's down my list here? I got A. How about B? Let me see who's in the B. Brendan Schmidt. Brendan.
Yeah, we are under reinforced.
There you go. Thank you so much. So we are under reinforced. And while you're here, Brendan, is this a good thing or this is a bad thing?
I believe you said it makes us happy.
Yes, so that is a good thing. You are absolutely right. So what it tells us, we want our beam under reinforced. Okay, we want our beam to be under reinforced, preferred under reinforced, so we can utilize the strain in the steel full ductility. What that mean? That means we have time to run. We have time to escape when something bad happens. Okay, so keep in mind, we like phi equal to 0.9. We like phi equal to 0.9. So we want strain in the steel got to be greater than 0.05. That is preferred. That is preferred. Okay, so not too bad. We are arriving at a safe zone here, right? But to finish the calculation, keep eyes on the ball, right? What are we looking after here? We are looking after the calculated design moment. That is MN, nominal. Again, let me write it down. It's the first time you've seen this. So nominal moment resistance, okay? Or nominal flexure strength, whatever you call it, right? So that, ladies and gentlemen, has to equal to tension force multiplied by the lever arm JD. Okay, or if you hate to use tension force for some reason, you can always use compression force as well, use JD, but nevertheless, let's use that, right? Let's use that. So you have tension force, which is ASFY multiplied JD, and that is DS minus, and my next victim here, Carly, I'm sorry, Callie, Miss Hall, are you there? Hello?
Yes, hold
Hey,
on.
how are you doing, Callie? You okay?
Yes, I'm good. How are you?
Good deal. Well, I'm still here, alive, right? Pretty happy. So the lever arm JD
Yes.
now equal to DS minus something, right? So minus
It's
what?
the A over 2.
Exactly. Thank you so much, Kelly. That is the lever arm. Okay. I want you to remember this just like Kelly did, because this will come in handy in the exam. You won't have time in exam to flip through your creep sheet. This creep sheet is only help you to remind you what we have learned. You need to do this in your head. Okay. All right. So Mn equal to that. As it's not too bad. ASFY I calculated before is 190 kips of a total tension force. And the depth of it is 17.5 inch. And A is 4.6 inch divided by 2. So I have my number here equal to something. And all of you guys, folks, I give you 5 seconds, let's say 10 seconds, right? Your finger might be a little bit numb from coldness this morning to help me calculate this out, okay? Let's count for 10 seconds, okay? And see what you got. 10, 9, let me give myself a coffee, all right? 8, 7, 6, 5, 4, 3, 2, 1, 0.5, 0.4. Drew. Drew.
2000.
Hello.
Oh,
How
my
much?
bad.
How much? No, you're but now, but I heard the word 2000 what?
2,882.
Ah, great. Wonderful. Okay. So what is a unit, my friend? What is unit?
Kips.
And
Inch.
inch. There you go. Thank you so much. Okay, so that is the total moment. Thank you, Drew. And are we happy with this? Sure we are, but do I get a second? You guys all get this number? Feel free to jump in.
Yeah, I Yes, got that.
that
Want it
too.
in Kip's feet though.
All right, keeps feet, right? That's the next step. Thank you so much. So you convert by a 12 foot, sorry, inch foot, right? Inch per foot to convert it into a foot, right? And now what you get?
240.
240, exactly. Thank you so much. And that is, ladies and gentlemen, our final answer, 240 kips. I don't even bother second that because I know it. Okay, that is our, again, nominal moment resistance, or somebody like to say they're the same, okay? Nominal flexure strength, okay? Nominal flexure strength, potato, potato, right? Tomato, tomato, right? Same thing, okay? Same thing. All right, so we have that. Are we done? You find my next victim. Carson, Mr. Byers. Are you there?
Yeah, I'm here.
Hi, Miss Carson, sorry. Miss Byers, I'm sorry. So are we happy with this? Is this done? This is the design strength I'm looking at.
I think we're happy with it, but we might be asked something else.
Right, so what do we need to add? So something has to compare with MU, right? Right, so that is what? Let me give you a hint. What did we do before M? What do we do here? The strength reduction factor, right? Remember this? So what do we do here? Phi, come on, help me out. Phi what? Mn, right? That's what you do. All right. Sorry, am I scared you, okay? It's not that complicated. All my questions are simple, okay? All right. So that's what we need to do. Find out the reduced moment capacity. All right. So now the reduced moment capacity equal to what? Mn equal to phi Mn equal to 0.9 multiplied by 240 kip foot. So I'm gonna save you the trouble, 216 kip foot. All right, so this is the design flexure strength. Okay, thank you, Carson. Design flexure strength. All right, now at this point, we're done. But you may ask a question, what is MU? Well, I haven't given you the MU, right? Why is that? Because remember, this is only analysis. This is only analysis, meaning you were given the section, you were given the details, and you just have to find out the design moment resistance. You don't have to care about if the design is adequate or not, okay? You don't care about the design is adequate or not, okay? All right, okay, so we're good, right? But one tiny issue. Why tiny issue? What is the issue, Bob? I mean, everything looks fine and tidy. You know, what are you talking about? Here's my tiny issue. Remember when I said phi? Remember I said there's epsilon s slash t. There's a tiny foothold here. And remember I said this is what, 0.65, 0.9, right? My question is, why there's a slash of t here? Why do you want to put a t here? So this comes again from the strain diagram. This comes from again from the strain diagram. So if the epsilon Cu on the compressive side of the concrete is 0.03 at the failure, and then my strain here is epsilon s, right? Okay, this is perfectly fine if I have a section with one layer of reinforcement. Of course, the strain in that layer is the same for all of them. All right, and now I'm going to pick on my next victim. Let's looking for a D here. We're gonna have two D. Daniel. Danny?
Yeah,
Hey, how are you doing? Miss.
I'm good.
Good. So quick question for you. So here, the strain of steel, if I have one layer, right, they're the same. What if I have 2 layer of steel? That means if I have a 2 layer, right, let's call it layer 1, layer 2. Yeah, in the strain diagram, my question is that which layer has a bigger strain?
Layer 2,
Layer 2, why is that?
because it's on the bottom.
Exactly. Thank you so much. It's lower, right? So that is correct. So layer 2 has a larger strain. All right. So it's not too bad, right? It's simple, right? Of course. It's lower, so it stretch a little bit more, right? But let me see. Jacob Shantz. Jacob.
Yes,
Hey, how are you doing, sir?
I'm doing good. How are you?
Not too bad. So now Danny has answered the question correctly. So the lower layer has a larger strain. My question is, if layer 2 has yielded, so that means epsilon S2 has bigger than epsilon Y, is my layer 1 yielding?
Say not necessarily.
Not necessary, right? So unknown, right? Uncertain. Great. Thank you so much. Jacob's right. We don't know. We don't know. We don't know. So that is the problem. That is a problem. But if we say that layer 1 has yielded, for sure, layer 2 has yielded as well. Okay, so this become a question. What kind of question is that? We now know that the total strain or the average strain of this group of bars, it should be somewhere here, because that is the center of the group of bars. Is that right? That's the center of the group of bars. That means you need to pick which strain you are referring to in doing this phi here. So the question is that, is this epsilon S or something else? And in ACI, and this is ACI, again, 9.3, section 9.3, this says, look, folks, we're not going to use epsilon S. We're going to use epsilon T. Okay, epsilon T. Say, Bob, you're just swapping with something unknown with something else, right? What is this epsilon T anyway? Epsilon T, let me write it out, is the extremely stretched steel layer. Just my layman term of defining it. That means bottom layer of steel. Okay, bottom layer of steel. Okay, that means if I have a section, right? And this word bottom can be a little bit tricky because we now know that if I have bars and the bottom means the bars is in tension, right? This is on a positive bending moment, okay? So if I call this last layer, right? The strain in the last layer is called epsilon T, okay? And correspondingly, and this is new terminology, corresponding to the depth, okay, for the last layer is called dt, all right? And for the group of bars, if the center is somewhere here, and I'll show you how to calculate that later, but if the group of bars, the center is somewhere here, okay, and this for 2 layers or multiple layer is called ds, the depth of the section for multiple layers. And again, the strain at this point, okay, the strain at this point is called epsilon s, okay, epsilon s. All right, now I know I confused the bunch out of you, okay? You were confused and say, Bob, what are you doing? I just figured out how to do one layer and you threw so many layers. Now it's just one set of parameter D and epsilon, and those are 2 sets. What I'm going to do is that, now here's the differentiation. So when you calculate moment Mn, okay, I want to use color match, you see that it is T D S, okay, ds minus half a. You use the depths, okay, and I call it depths, okay, of the group of bars. So let's just say depths, okay, and put a bracket group, okay, because that is the in terms of center of the group of the bars, okay. But when you calculate the phi, strength reduction factor, remember there is equation something like this, 0.65 when strain epsilon T, correction, epsilon T smaller than 0.002 and 0.9 when epsilon T greater than or equal to 0.05 in between linear interpolation, right? And what is that equation? I can't remember. Let me just find it out. Where is my equation? Here. I think I wrote it down last time. Yeah, so here it is. Epsilon T minus that and that. So epsilon T. Okay, let me just finish that. Epsilon T minus 0.002 multiplied by 250 over 3. And that is for epsilon T. And this is mathematical symbol belong to a range, right? What is the range? 0.002, 0.005. Okay. So if I really want to put it, this is so-called over reinforced. This is so-called under reinforced. And this is so-called transition. Clear? That's clear? I think so, right? I think so. So differentiate. What I'm trying to say, when you use dt, okay? That is depth of the last layer of the reinforcement to find out epsilon T. Okay, you say why? How? Well, remember the strain diagram, epsilon Cu. There are two depths now, right? There's epsilon S, but there's epsilon T. So you use depth dt to find out, okay, to find out epsilon T, and you use the last layer of steel, the strain of that, to find out the stress reduction factor phi. And correspondingly, for the moment, you use ds, okay, and you find the stress in the steel. Make sure that is yielded, and then you do them. Okay. Two separate things. Okay, two separate things. All right. And if you were to decide which zone are you in, under reinforced, over reinforced, under reinforced, transition zone, you use epsilon T. You use epsilon T. I hope this is clear. Okay. Any questions, guys? This is dire important, okay? Much important than the password to your video game login, okay? This is direly important, okay? Any questions on this? No? All right, okay. So now one thing, for one layer or for single layer reinforcement, right? We are in luck, and that's how we survive so far. Because for a single layer reinforcement, sorry, single layer reinforcement, okay? Single layer means one layer reinforcement, okay? We got lucky because only under this condition, the strain in the steel epsilon S is equal to epsilon T. Hence, I cleverly put epsilon T, epsilon S slash T, right? That's how I did it. Did I do it? I probably don't have it here, but yeah, there you go. That's why I was able to do this, because they're the same for one layer of reinforcement. Okay, so we get by, we're fine. Okay, but we have a problem, Houston. We have a problem if the reinforcement is not one layer, it's two layers or more. Okay, two layers or more. Okay, so example number 2, and I'm just going to open it. Okay, we'll not be able to finish it, but we're going to open it. So lecture 3. So okay, let me get this thing going on here. Lecture 3. Okay, and that is example. Let me just put down here, lecture 3. Okay, and this is single steel, single reinforced. This single is different from the other single. Okay, this single means only tension reinforcement only. Okay, all right, and multi-layered reinforcement. All right, okay, so that's how we're going to do that. So that is trying to find M for this case. Okay, so take a look. I have a section like this. Okay, nice, beautiful rectangular section, and my favorite. Okay, and I have a width of it, say B, and I have a depth of it. Well, actually, now say depth, yeah, just say height of it, H, edge to edge, height of it, okay? And instead 1 layer reinforcement. Now I have 2. And to make things just simple, I have 4 number 9 bars distributed just like this. And they're all number 9 bars. So 4 number 9 bars. Okay. All right. I'm going to pick my next victim now. I got J. I'm moving to M. So Megan. Hi there, Megan.
Hi,
Hey, sorry, you're my next victim. How are you doing, Megan? Doing okay?
I'm good. How are
All
you?
right. Still alive. Can't complain. All right. Quick question for you. For number 9 bar, what would be my diameter of number 9 bar? Okay. What is my diameter for number 9 bar?
1.125 inches.
Exactly. So that is 9/8 of inch. Wonderful. Thank you so much, Megan. So now you also know where you're having this. What is the area for number 9 bars?
1 inch squared.
1 inch squared. Great. Wonderful. All right. So that is what we need. Okay. So now I have all the dimensions at my disposal. And to sweeten up the deal, I tell you that, look, I have a concrete cover for the bottom reinforcement that is 2.5 inch. All right. I use 2.5 inch plus the chairs. And then I put a spacer between the top layer and the bottom layer at a 2 inch of distance. And now this sets me up a 4.5 inch of cover for the top layer. All right. Okay. Now the question is, what is DT? So example. Okay. Example. The question is, given the section below, what is my DT and what is my DS? Okay. All right. So again, what is DT? DT is the distance between the top fiber to the extreme bottom layer of the reinforcement. That is simple, folks. So DT should equal to what? H minus 2.5 inch. And that is, say, if H equals 20 inch, make things easy, and B is 12 inch. So that is 17.5 inch. Great. Okay, no problem. But what is DS? Well, I don't know, Bob. What is DS? Is it somewhere in the middle? Here, for example? Sure. But how do we determine that? How do we arrive at this number here? How do we do that? We use the famous equation for finding the centroid. How are we going to do that? Well, let me tell you. So instead of calculating DS directly, I'm going to calculate the distance between the centroid and the bottom side, and I call this y bar. Okay, I call this y bar. And I know that y bar should equal to summation of area of each layer, and this I representing each layer, okay? Layer, okay? And distance of layer to the bottom line here and divided by the total area of the reinforcement. Okay, all right. Instead of this, oh Bob, this is too much, right? This is too much. Can you be more specific? Can you be more specific area of each layer? Okay, I say, yeah, sure I can. So y bar in this case, how many layers I have? 2. Top layer, I have 2 number 9 bars, so easily 2 inch squared multiply the top layer distance is 4.5 inch plus bottom layer 2 inch squared and multiply distance 2.5 inch divided by the total 4 inch squared of steel. And that, ladies and gentlemen, gave me something. And please help me out using your calculator to get it. Okay, I'm gonna again give you 5 seconds. Maybe this is short, right? So let's see what you got. 5, 4, 3 potatoes, 2 tomatoes, half sheep, quarter lamb legs. I don't know, start getting hungry. I'm getting some numbers. So let me see who's my next victim. Paul. Camp, is that Camp? Are you
It's
there?
nap.
Nap.
Okay,
Thank you so
silent.
much. Okay, silent. Great. I learned something. Okay, Mr. Knapp. So what do you get for Y bar?
I got 3.5 inches.
3.5 inch. Thank you so much. Do I get a second? Anybody else? Anybody
Yes.
else? All righty. So not just me and Miss Knapp here. We have everybody agreeing, almost one guy, 1 bar, 3.5 inch. And that is the correct answer. So given that Y bar is 3.5 inch, so I can say now DS equal to H minus Y bar, and that is 20 minus 3.5 inch, and that is 16.5 inch. So that is the depth of the section. That is the depth of the section. Okay. All right. So now we know how to calculate the centroid, of a multi-layered reinforced section. Okay. So how do we calculate the moment? How do we calculate the moment? All right, let's proceed. Right. So next question. What about the moment? Right. What about moment? Okay. And to do that, I need to know the properties of the material. So at prime C, let's just say curbside concrete 4 KSI, and I would say that a grade 60. And again, this means that yield strength of the bar is 60 KSI. Don't forget. Okay, and I need to find MN, and where I'm at it, I need to also find my strength reduction factor phi here. Okay. All right. So how to solve this problem? You say solve. Very confident, right? Although we may not know the exact number and what happens, I can start my journey, right? So solve it first. What do you do? First, what to do? I need to compute. Okay. Effective compressive zone A, actual compressive zone C, and strain in the bar epsilon S. Okay. Epsilon S. Okay. Slightly different. Okay. Now A should equal to beta 1C. And that is equal to ASFY, just like we did before, tension force divided by 0.85 F prime C B. Okay, so how much reinforcement area I have? 4 number 9 bars, so 4 inch squared, and yield strength 60 KSI. Okay, divided by a 0.85 4 KSI of concrete and 12 inch of width. Okay, so now again, 5 seconds. What do you have? What do you have? 5, 4, 3, 2, 1, 0.8, 0.6, 0.4, 0.2, and Natalie.
I've got 5.88 inches.
5.88 inches. Do I get a second? Do I get a second?
Yeah.
All right, good deal.
Yep.
Okay. All right. So now we got that 5.8 inch. Okay. All right. So with that, I started to do my C. Thank you. And that is my actual compressive zone. So A divided by beta 1. Knowing it's 4 KSI, I'm going to use a very simple number, 5.88 inch divided by 0.85. And what do I have here? Owen, McGuire, Owen.
Hello.
Hey, how are you doing, man? Doing okay?
Doing good. How are you?
Still alive, can't complain. So where we're at it, what is my actual compressive zone size? C.
6.92.
6.92 inch. Do I get a second, folks?
Yep.
All right, thank you so much, Ms. McGuire. And we have this.
Oh.
Okay, we have this actual compressive side. Thank you. And now with that, I want to get my 20% point. Remember? I want to get my 20% point. So I drew the diagram, but I'm lazy, right? I don't want to draw it all the way where I'm having you guys here. So I'm just going to draw my strain diagram first. Okay, so this is epsilon Cu equal to 0.03. And then I need to get my stress strain in the steel epsilon S. And knowing that I have 2 layers, so I have a bottom layer epsilon T as well. Okay, now the actual compressive zone C is right here. Actual compressive zone C is right here. Okay, and now the depth of it. Okay, I have 2 depths now. One is called ds. Okay, and the other is called dt. Okay, but never mind, let's go ahead, epsilon t equal to a dt. Okay, now you may be asking, so Bob, you're talking about epsilon s here, right? So why you're starting to epsilon t? Well, I can do epsilon t first and do epsilon s, right? But let me just correct that. Let's do this and this for both. How about that? Okay, so dt minus c divided by c multiply epsilon cu, and then epsilon t equal to dt, and that is 17.5 inch minus c, which is 6.92 inch, divided by c, 6.92 inch, and multiply 0.003. And again, folks, need your help here. Didn't do the calculation. Sorry, I didn't do my homework. My dog is pretty big, ate everything, right? Ate everything. So let's give some time, 5 seconds maybe, and we're gonna pick my next victim. So 17.5 minus 6.92 divided by 6.92 and multiply 0.003. And Peyton,
How's it going?
hey, how are you doing, man? I'm fine. So can you help me out
Great.
here? Yeah, great.
Yeah, I got
Okay.
0.0046.
0.0046. Great. So do I get a second?
I also got that.
Alrighty. Okay, so we're good. So that is the strain in the steel. So Peyton, you're not off the hook yet, sir. Where we have you? You look at this number. What do you feel? Do you feel anything at all as a good fellow civil engineer?
I don't feel amazing because it's below that 0.005 number, right?
You're exactly right. You're a wonderful civil engineer, right? So you saw this, your heart sunk and say, oh crap, I'm just hair less than the tension control limit. This tells me that I'm in a transition zone. Okay, wonderful. Thank you so much. You're officially off the hook now, sir. So that is what's happening. Okay, so it's not in the transition zone. But in this case, we're pretty happy. That means at least it's yielded. Okay, so I can proceed with that calculation, right? Proceed with that calculation. And then we'll talk about the next lecture, but so supposedly you can just carry on, find your phi mn and everything, right? Knowing that it's in transition zone, phi has to be somewhere between 0.65 and 0.9, but it's not gonna be either, okay? It's gonna be somewhere in between. All right, okay, this is it for today, okay? Thank you, folks, and I'll meet you guys on Monday. Now, one thing, I might be traveling next week. So if I do that, I'll know that by end of today, depends on the weather and everything. But if I'm traveling, we'll do this online for 1 week only next week, okay? Let me repeat. If I'm traveling, we will only do the online thing for 1 week next week, temporarily, okay? All right, if I do that, I'll send you reminder notes. You should be seeing these notes on Canvas and record a lecture on my YouTube channel as well, okay? Thank you very much. Please stay behind if you have any question on the homeworks or lecture contents, okay? Thank you and see you on Monday next week.
Thank you, Professor.
No problem. See you next week, man. All right, folks. Now it's your time to throw in the jabs. Any question about homework? Drew, as you open up your mic. You there, Drew, or your ghost?
Drew, we can't hear you.
Okay. Mind you that we're in recording. Okay. Anyway, any other questions for the homework or lecture content, folks? Anything?
I had a question on the homework.
All right.
It's kind of in terms of the formatting. So
Oh.
I know you said you needed it to be on engineering paper specifically.
I prefer. Yeah, I prefer, but if you don't have that, A4 sheet is fine, but please organize them. When I say organize, you put them in one line, so I won't read across lines. You know what I mean?
Okay.
Yeah.
And then for boxing our answers for problem 5 and 6, even though they're written and everything we're doing for that pertains to our answer, do you still want us to box it?
Hello.
Oh, let me see here. Okay, maybe I can pull out the exam. Give me homework. Give me 1 second. Stop sharing this.
Is my mic working now, guys?
Oh, okay. I see.
All
No
right,
worries.
cool.
Yeah, it's working now.
All right,
Yeah.
I'll ask my question after.
Okay. 1 second, let me pull out the homework. Okay. For spring, homework 1. Let me see this. Give me 1 second here, share screen, and we're here. This is the one you have, right, guys? I have a different version, right? So you're talking about 5 and 6, right?
Yeah.
Okay, so yeah, it's grade 60, right? I think. And you just talk about this is yield strengths. And if it's just one sentence, then it's just verbal, and you don't have to box it or anything. Just answer the question.
Yeah, I just know that question 6 had like lots of different multiple questions in it, and so
Oh, okay.
I took up a bit more room for that one.
Oh, okay. Yeah, well, it's more like how to say this is more like a verbal, right? No equations and everything, just some joins and figures. So yeah, I think you can just write it up, whatever format you want. When I say box the answer up, it's just mainly for these calculation problems.
Okay, I just wanted to check. So.
Yeah, no problem. Yeah, that's good. Okay. Drew, you have questions as well?
Yes. So
Okay, go ahead.
I'm a little confused conceptually where under when we want something to be under reinforced.
Oh, okay.
And
let me switch.
it I guess in my mind, what I have right now is that so whenever you're putting a force on the concrete beam, that we're trying to calculate this strain factor of the steel whenever the concrete is going to bust, right?
Yeah. Well, you think this way, no matter what you do, the concrete have to crush at the end of it. So concrete crushing is a given. Okay.
And then, okay.
Yeah. So now the game becomes how much of reinforcement you have utilized, right? So how do we judge that? If we utilize a lot of strain, deformation in the reinforcement, we call it under reinforced. Okay, and that's good. But if you put too much steel there, you end up not enough of straining in your reinforcement. Why is that? Because you put a lot of steel in there, so your total tension force is high. So you only need a smaller area for compression to balance that, right? And then you end up with a strain in the steel that is low. And when you have that situation, strain in the steel is low, you're not fully utilizing the capacity or capability of the reinforcement. So you over reinforce the section.
Okay, so then when we're under reinforced, that's the zone that we're in whenever the compression and tension are supposed to balance out.
Moved over than that is tension control limit, right? So your strain has yielded and also bigger than 0.005.
Okay, and that's when. Well, so in my mind, I'm saying that the tension force is going to be smaller in that case than the compression force.
No, when we say the balance, right? That's a good question. I see where you're getting at. So when we say balance, that does not mean the equilibrium. When we say balanced, at that point, we're just saying when the strain in the concrete has busted, the strain in the steel just reached the yield strain of 0.0207.
Okay.
In whatever scenario, under reinforcement transition, whatever, the equilibrium that the total compression has to equal to tension force always. That has nothing to do with the strain or not.
Okay. So then, sorry. Maybe I could come in during your office hours. I'm trying to visualize all this in my mind, and there's a lot of pieces. Then I would have to ask.
I can do that right now. I think because I feel you. I feel you. I mean,
okay,
I was in the same bind before. Here, look.
If the concrete busts, right? I mean, that then would mean to me that like the whole entire beam has pretty much failed. So why would it matter then if the steel is allowed to continue to elongate?
The steel will, we don't really care whether steel continue to elongate. Okay, so we only care about at failure, at concrete bust. Do you see the picture here? Right. So we only care about at the concrete is busting, right? What is the strain in the steel? So in another word, at failure, has the steel yielded or not? Why that is so important? You think of it, if say if your strain in the steel is lower than 0.002, let's just do something extreme, right? That means that your steel is elastic. So in terms of stress strain curve for the steel, you're at this point, somewhere here, right?
Yes.
Lower than that, right? So
Okay.
that means that when you're concrete bending, you're failing it, right? Before it reaches the failure, you don't see anything on the surface. There's no cracking, there's no nothing, because the deformation is still so small. Okay, so if at failure, meaning at the final failure, the strain in the steel has already hit 0.05 or anything big, you will see a big crack.
Oh, so we want to see a crack.
Right, because you want to give
Oh,
a, yes,
okay.
you got it. You want to give a warning, right? If you look, it's ugly, it cracked a lot, and you see the naked steel exposing like a bone, right? You better run.
Yeah.
Right. That's where we're getting at.
Okay. All right. Okay.
Good deal. Yeah, good deal.
And so the transition stone is we'll see a crack. We'll see a little bit of a crack then. Is that the idea?
Right. So if you're in the
okay.
transition zone, I mean, you before failure, you'll see some crack, but not so severe.
Gotcha.
Right. If it's over reinforced, you don't see a whole lot of crack at all. It just go from looking nice, and the next moment, concrete crash, kapoof, everything's gone. Right. Then
Gotcha.
you don't have time to run.
Gotcha.
That's
So
okay.
I'm sorry to jump in here. This is also my question.
Okay, good.
So you're saying that if it's over reinforced, there's not a warning?
Yeah. Well, I'm not saying there's not a warning. It's just everything's brittle, elastic.
Brittle. Okay.
Yeah. So I can put this way actually. Say, let me try to draw it. So how about this? If you imagine you have a concrete beam like this, and you put a reinforcement underneath, right? And you do a simply supported condition. That is, one is roller and the other is pin. You bend it like that, say 4-point bend, right? You load it like that. Say these are the failure curve you're gonna see. And let's just say force versus displacement. If you're over reinforced, what you end up seeing is something like this. Goes always like linear line, and at the bottom failure is a little bit curve here, and then drop like that. Boom. Okay, so this is over reinforced, too much reinforcement. Okay, and now if it's say transition, yeah, you have some linear line, and then you have some nonlinear curve, and you do like that, and this is transition. Okay, but if you have under reinforced, it goes something like this, and then goes like that, and goes, then poof. Okay, so these period, or this so-called plateau, red a little bit largest, black a little bit smaller, and for the blue one is nothing, basically, right? These are so-called ductility. Okay, so that means, when you see the beam start failing, you experience a lot of deformation or deflection already, right? The beam is sagging, basically, and you can visually see it. Right. So you want this, right? Because, when you see this and it's going to sag, as the beam become like this already, right? Big cracks here, right? The bar holding up together, you can run. But for over reinforced, you don't see this at all. It goes from a very small deformation here and then just kapoof, gone. Right. That's the difference. Do I answer that question to you as well?
Yeah, I think I'm getting it. Oh, sorry. I think you're asking something else, though.
Jessica. Yeah. Oh, sorry, Ryan. Yeah. Make sense?
Yes, thank you.
Yeah, no problem. Yeah. Jessica, Natalie, any other question you have?
I don't have any other questions. I just wanted to sit in and listen.
Okay.
All right. Thank you, Dr. Chen. I gotta go.
No problem. Yeah. Have a good day.
I had a quick question. So
on like problems 1 and 2,
okay, let me
we're talking about.
Give me 1 second. Let me switch to the problem. Where's my Adobe? Where is it? Give me 1 second. Here we go. Yeah, 1 right here. Okay.
Yeah.
Uh-huh.
So it asks for the factored reactions.
Factor reactions, right? So you have this PU, right?
Yeah.
So first of all, when you see U, that is already factored, isn't it?
Yeah.
Okay, so if you find reaction forces under PU, that is already factored as well.
Okay, that
Right.
was basically my question. So we're just finding, since the forces themselves are already factored, we just basically need to find the reaction
That's
from
it.
this diagram.
Yep, you got it. That's it.
Okay.
Okay. Yeah, this is just testing you whether you know the definition of the U or not. Okay.
Okay.
Yeah.
All right. Sounds
Yeah.
good.
No problem. Yeah. Anything else, folks? Ryan, you good?
I just have a logistical question. Would it be
Uh-huh.
possible for you to post the lecture notes before class so I could take them before class and just add to them during lecture?
Yeah. I think I have done that. If not, you can double check. Usually I post last year's lecture notes before class.
Okay, yeah, lecture 3 just wasn't on there when I checked this morning.
Oh,
Maybe you-
okay. Yeah,
so
I think I went a little bit fast today.
Okay, sounds
Yeah, no problem. I often do that. So I apologize. I should have uploaded a video last night. I just haven't gotten around to finish some editing yet. But I'll upload the previous last Thursday lecture, recorded lecture, because on Monday is not much going on. You don't have the screen and everything. But I will upload last Thursday's lecture and today's lecture fully recorded and everything, and all the notes from last week and this week, as well as like the previous semester notes. I will do is I'll create a folder, say previous notes, and you can go there and take a look what we have learned. So do a pre-learning if you want.
Okay, awesome. Thank you.
No problem. Thank you. Okay. All right, Natalie, you good? All right. Okay. I assume you're good. Okay.
Yeah, I think that's all I needed.
Okay, no problem. I see you guys on Monday. Okay. All right. Thank you so much. Take care. Okay. Bye now.
Bye.
Mhm.